Alright, welcome. In this video, I'm going to be providing a little further discussion on the alternating series test. And maybe you asked me, do I really need the terms to be decreasing in magnitude? Or maybe you're just wondering that question. And the answer is yes, we really do need the terms to be decreasing in magnitude in order to apply the alternating series test. Okay, and I'm just going to show you a quick example that was shown to me that I think really set me straight on it, because I've had doubts on this in the past, I will admit. But suppose you've got a sequence where the first term is 0, and then after that, it's 1 over n if it's an odd, like n equals 1, n equals 17, something like that, and 1 over n squared if n is even. Okay, and then we're going to consider the sum, like the alternating sum with these terms. Okay, so sometimes it's 1 over n, sometimes it's 1 over n squared, right? And it's going to work out that the negatives are going to go with the n squareds. That's not true. Those are the positives, and the negatives go with the 1 over n's, yeah, the odd terms. Okay, so I'm going to write out this terms of the series. Fortunately, like when I wrote them out earlier, I did it right. I'm going to write out the terms starting with n equals 0. Well, a sub 0 equals 0, and negative 1 to 0 is 1. So start with 0, negative 1 to the first times a1. Well, a1's 1 over 1. And then I just keep writing out terms, and I just kind of see the pattern. It's like, okay, great. Now what am I supposed to do? What you're supposed to do is kind of group the terms 2 at a time and see if we can rewrite with kind of a different rule besides negative 1 to the n, a sub n. So I'm going to grab 2 at a time and say, all right, thinking about this, okay, well, it's like 1, 3, 5, and 7 along with 2, 4, 6, and 8. I can make up a rule for that. That would be like n equals 1 for the first one, n equals 2 for the second one, n equals 3 over here, n equals 4 there. And the easier one to see is that the number that's getting squared is 2 times n. But the number that's going in the denominator of the odd index terms, okay, like 1 over 1, 1 over 3, 1 over 5, 1 over 7, that's going to be 2n minus 1. So I'm going to start off with the negative terms. That's like a negative 1 over 2n minus 1. You can stop and check and make sure that works. It does. Plus, I've got all these positive terms, 1 over, and I'm squaring 2n. So I'm going to put the 2n in parentheses and then square. I'm going to do some algebra, right? I'm going to simplify that 1 over 2n squared. That's going to be 1 over 4n squared. And I'm going to put the one with the positive coefficient in front. Okay. Now I'm going to need to combine these with a common denominator. So the 1 over 4n squared, I'll be multiplying that by 2n minus 1 over 2n minus 1. And I'll get this, right, with a common denominator, and then I can kind of simplify the numerator and also distribute out the denominator and get this, right? Okay, so I've got negative 4n squared plus 2n minus 1, and then in the denominator I distribute the 4n squared over the 2n minus 1, and I get that. Okay, now I'm going to rewrite series S using this new formula, and n starts at 1, because we just started by adding a 0, so we don't really need to do that. I can say now S starts at 1, goes to infinity, negative 4n to the 2 plus 2n minus 1 over 8n cubed minus 4n squared. And I'm looking at that, and it's degree 2 in the numerator and degree 3 in the denominator. And if we see polynomial in the numerator and denominator of a series, in terms of a series, we're going to want to apply the limit comparison test. And you can see it's net bigger on bottom by 1 power, much like the harmonic. So I'm going to say this can be shown to diverge by limit comparison to the harmonic series. You know how to do that. You know how to write out your bullet points and check your conditions and do all the stuff. We know what's going to happen. We're going to limit compare to the harmonic, which diverges, so that S also diverges. So in this case, even though the terms are alternating and their limit is definitely 0, they are not uniformly decreasing in magnitude, and we are not having convergence on this particular series. All right, so that's it. That's really all I got for you. This kind of quick counterexample. I really just made it kind of just to have at the ready in case somebody wondered or was asking the question. So that's going to be all for this one. Thanks for watching.